Good afternoon. So this is the last session, and it's a pleasure to welcome. Andrea Gambassi from CISA, and he'll talk about transport of bosons and fermions in 1D unified picture.
So first of all, I would like to thank the organizer for having set up such a beautiful meeting. So I was a bit hesitant about what to talk about, because in principle, I could have talked about stochastic dynamics of particles in correlating fields, showing you the emergence of a nonlinear Langevin equation, memory effects, nonlinear dynamics, monotonic relaxation in dissipative system, even stochastic thermodynamics of fields. But, you know, I gave this talk in Florence, probably. Otherwise, I could have told you something about anomalous diffusion of chemotactic particles, so in active matter, which is also an interesting topic. But then I thought probably, then I could have talked about statistics of first detection times in quantum mechanics. But probably also this one, or Casimir-like forces in flocking active matter, given that there is such a large interest in active matter. But then I decided to go with something which has to do with Italy, so I have to talk about fermions, and also to the place where we are, bosons. Unfortunately, there are no Ramons, so otherwise I would have talked about it. So, and actually, I mean, my aim now is to keep you awake more than that. So it's going to be something a bit light. I mean, I hope entertaining with lots of movies and things like this. So actually, I will talk about dissipative transport of bosons and fermions, a unified picture, and the unified picture is KPZ. So also because I'm in this session, I thought this was the best topic. So what do we know? I mean, we know that with the progresses of ultra-cold atomic systems, nowadays it's very easy to produce in the lab optical lattices and then to load other bosons or fermions in these lattices. And this has been a very successful platform to study also collective phenomena, the Bose-Hubbard model, the Fermi-Hubbard model. So it's a playground of current experimental physics. And typically, this system, they have a certain probability amplitude to jump left and right, and then depending on the relationship between their interaction and the hopping rate, you can observe different kind of phases. Now the question is, we would like to make these bosons to pull them somewhere. So the first idea is simply, well, you tilt the potential, no? Unfortunately, it doesn't work because, you know, differently from dissipative systems, these are conservative. So if this guy hops here, because of conservation of energy, he has to come back. The Wannier-Stark localization. So it's not enough to tilt a potential. In order to make this boson or this fermion really move in one direction, what you need to have a bath which is able to take out of your fermion certain energy and make it progressing to the right. So, or maybe make it directly to do the transition from where it is to the next site via sort of incoherent topping. And if this bath has sufficiently high energy, can give a sufficiently high temperature, it can be also able to provide energy to jump in the opposite side. Actually, I will, from now on, I will sit in the case in which the bath has a low temperature, so the particle will go only one direction, to the right. So this can be realized actually, you can see that if you consider bath of background Bose-Einstein condensate of phonons, essentially you can represent it as a bath which couples linearly to the occupation number of each site of this lattice, where x is the coordinate of the bath. So you do a certain number of things. You can write the interaction between the bath and the system. You do the rotating wave approximation, whatever you need, and you end up by saying that the density matrix of this object has to follow this Lindbladian evolution, in which A and A DAG are the creation annihilation operator of either bosons and fermion, and there is a rate to gamma plus to hop to the right and gamma minus to hop to the left. In this system, because of this incoherent nature of the tunneling, the coherent part of the Miltonian is actually negligible. You don't need it, okay? So, and as I said, from now on, I will focus in the case in which these bosons, these particles, sorry, are pushed to the right, okay? Sorry, my voice. So this means that if you start with a initial density matrix, which is diagonal, the evolution will keep it diagonal. And so this means that you can diagonalize the density matrix in the Fock spaces of the basis of the occupation number of the sites, and therefore essentially you have simply to study the probability, evolution of the probability that you have a certain number of occupation, that you have a certain occupation number, sorry. So you can imagine this lattice with the lattice sites and the occupation number at each side. When you do so, the Limbla become a classical master equation, which, taking the result from the quantum mechanics, it takes this form, where these t plus and t minus are the shift operators acting at site I. Takes this form. So you sit down, and the sign, from now on, the sign plus is for bosons, the sign minus is for fermions. You have to take into account the statistics. So now for fermions, now if you unzip these things, you sit down and you unzip this master equation, you discover that for fermions, this master equation does not allow jump backwards. I mean, we knew. So this is an asymmetric process. The probability to hop to the nearest neighbor unoccupied site to the right is simply gamma dt, simple. And then there is exclusion, so you cannot jump being a fermion on a site. So you see, essentially, this is the ASEP, of which we know already many things, okay? While for bosons, so if you unzip this writing, you discover that it cannot go back, fine. And then the probability to jump from a site occupied by ni individuals to a site with ni plus 1 is simply gamma dt ni times this bosonic enhancement. So they like to stay together, no? The more bosons you have in front, the more you want to go there. The zero range process would correspond in the case in which the factor is not there. So this we call this model ASIP. Actually, then we discovered that it was already studied in a completely different context. Shlomi, I'm sorry, this is not the ASIP that you introduced, but we called it ASIP. So we have the system, and we can say that essentially we can unify the probability, the transition rates by saying that the probability to go from ni to ni plus 1 is gamma dt ni 1 plus or minus 1 ni plus 1. Okay, so we have a unified picture with this unified form. So what do we do next? We do numerics. And we are interested in the transport property. So the question we would like to ask is, what is the statistics of the number of particles which is, goes beyond this side of the lattice? Okay, I load my lattice with all the particles in the lattice space, and here I let them go. So with ASEP, I mean, I promise movies, so now we watch the movie for 20 minutes, and then we're done. So, they go one by one, by one, by one. You start, there is a certain rate to go to the right, and then you expect that at a longer time, the average number of particles will grow linearly. I mean, what else? I mean, there is a certain rate to go, okay? The ASIP, the dynamics is completely different, you will see in a second. It starts doing things like this, It creates these bumps, there is sort of condensation, they go ahead, and they go like this. But also here, you see that the number of particles, I mean, most likely it will grow like time, okay? And so this is indeed the case. What is interesting is that when you do a quartz grain picture, or if you want to do the spatial average, you discover that for the ASEP you have this kind of profile, sharp, and then as time goes by, smoothens. While for the ASIP, indeed, as we saw, you have this shock front which proceeds, okay? If you want to be quantitative, you plot NR as a function of gamma t, and you see that indeed in both cases, these are different realizations, different colors. You see that in both cases it grows linearly. And then the next thing to ask is, what about the fluctuations? Well, when you measure the fluctuations, they also look similar. Okay? Yes?
Why is the area not conserved in the boson case? In the lower plot, we have the same number of particles. Right?
No, it's conserved because what you gain here, you miss here. And in the bosons?
In the boson case.
Because you have the guys coming from the infinite, yeah. And actually, we expect, it should be a surface growth. We know it should grow like t to the beta. So this process, they are clearly different in the realization, but they start looking similar in some of the features. Okay. So the first question is, can we understand why these shapes and so on? You can do well. You do first. Let's try to understand the mean transport. We replace the occupation number with a space-time dependent thing. You can do it properly, as Herbert teaches us to do with doing coarse graining, but you can do also in a more direct way. So you have the local conservation. You will know that the density is going to be a function of the overall density, of the local density of the particles. And then what you can do analysis of the steady state plus nonlinear fluctuation hydrodynamics, again, as Herbert told us to do. Or, if you like, you can do the Fokker-Planck approximation of the master equation. You expand it, you will discover an effective Fokker-Planck equation. In both cases, you discover that the current is simply gamma n 1 plus or minus n, which is nothing but the mean-field version of the transition rates. So the equation then, which is followed, combining the two, is nothing but the Cauchy-Burger's equation, okay, with the plus for bosons and the minus for Fermi. This is already quite a lot because this allows us to understand why it's linear and why they have these shapes. I mean, I will give you, given that there are many students, I show how you Pullman approach to get these things. So if you rescale time, you see that the equation for the ASEP, you can write it in this form. If you start with an initial step like the one I showed you, this coefficient in front is telling you how much your dynamics is trying to pull a point. So if you plot this velocity profile at this point, you see that it's pulling the guy at low density in this direction and pushing, you know, like this. So it's not surprising that eventually the shape will be something like a stair like this, which expands with a velocity gamma t, and therefore the number of particles which are to the right will grow like t. While so this we understand. For the ASIP, instead, you write down the equation, you do the same game, you plot this function, this velocity, pulling velocity as a function of the density, and you discover that the guy at higher density are pushed more. So, I mean, clearly they cannot overtake the other guys, so you expect that this will give rise to a shock wave. I mean, clearly all that can be done mathematically rigorous, but this is the Pullman approach. So there will be a shock wave which has a certain velocity in that direction, and you can write the equation as a continuous equation, clearly. And essentially, the intensity of the current coming from the right fixes the velocity v to 2 gamma, okay? Because you have to. So also here we have understood. So far, so good. What about fluctuations? Well, fluctuations, we go on in the scheme. So we add a diffusion term, but then we have, if you want, this is also a friction term. We have to add also a noise, friction and noise. And what are the properties of the noise? You can calculate, as I said, with the two approaches that I mentioned, and you discover that this noise has to be Gaussian with a certain diffusion coefficient, and you end up with the stochastic Burger equation. Stochastic Burger equation, which we studied. So in this particular, it is known either by solving the ASEP exactly or via what is known the scaling behavior of the stochastic Burger equation, that the number of particles grows like beta with 1/3, okay? So then we understand, at least for the ASEP, this 1/3. I mean, actually, I remind you that the zero range process, this would be 1/4, because these two guys, they are going to have more or less the same beta. They are going to have the same beta, so one may wonder, but do you get always the same? No. For another process, you will get a different answer. So, and then the question is, let's go, then focus on the statistics. So we look at the number of particles which are to the right of the step. Then we said it grows linearly. So there is a width which grows like t to 1/3. Now we focus on this random variable here, which we hope is going to be a stationary variable. What can we say about the statistics? Okay, so if you want, what is it's the probability density? For fermions, we know, I mean, either from ASEP, we know that this is the Tracy-Widom distribution of the Gaussian unitary ensemble. This has connection with random matrices. In the audience, there are experts in random matrices much more than me, but from the practical point of view, just a distribution with this name, okay? This is known. Now the question is, what about the ASIP, the bosonic version? What do we expect? Well, we will have the typical fluctuation, as usual, the one in which there are too many particles to the right, so NR exceeds a lot the velocity, or when they are of order 1. No. So how can we understand these two limits? So let's look at the rare transport for eta going to infinity. Means I want to have on the right much more particle than the typical, okay? So I remind you that it goes like this. So essentially, it proceeds via a moving shock wave. In order to have many more particles to the right, what you have to ask is that this shock wave, so it carries much more current than usual, okay? So the question is, can we have a number of particles which grows in time linearly with a velocity which is much larger than the velocity v appropriate for this process? So note that when this happens, the eta scales like t to the 2/3, because in any case, this is linear, this is t 1/3, you end up with something which grows like t to the 2/3. And then we understand this limit. Now, imagine we have our shock wave. We want to have an extra current. So the extra particle which make the extra current will pile up probably in front of the shock. And now you have to ask that essentially this wave proceeds as a whole together without spreading, okay? So essentially, if you call now P1, the probability that in a small time dt, this wave rigidly moves by a certain amount, essentially what you have to ask is that it proceeds with step by step. So the probability to get this velocity, this higher current, is simply a product of P1 and that you carry this wave. But so it means that it's P1 over the t over delta t. Or if you want, is the exponential of t. But then if you remember that t eta scales like t to the 2/3, you immediately get that the exponential goes like to eta to the 3/2. So we understand that tail. So on the other end, we can ask the rare transport at the opposite. So the rare transport at the opposite is when you don't transport anything. So what does it mean? Again, even if you don't transport anything, eta goes like to minus now t to the 2/3 for the same reason. So it means that this shock wave doesn't move. And how is it possible? I remind you that if you have a column of a zero particle at the site, the probability for one to jump ahead is gamma and not t. So the probability that nobody jumps is 1 minus gamma and not dt, so which is p naught, where p naught is something, to the power n naught. So the probability not to jump grows decreases like n naught, okay? So, and if this wave, this shock front should not proceed, it means that if you have all the particles, this one doesn't go beyond. And this happens with probability P naught. But meanwhile, others are coming from this side, and they have to pile up at the border. So then you will have two particles. The probability that two particles, none of them jumps is P naught squared. If you have three, then another come is P naught cube, and so on and so forth. So you see that the probability that no particle jumps beyond the border is simply the product of this probability. Or if you want, you have to sum the integer numbers at the exponential, so it goes like t squared, exponential of minus t squared. You remember the relationship between t and eta, and you discover that this is the shape, okay? So what about the full statistics? For statistics, you do numerics. Okay, from fermions, again, this is known, and these are the plots, so the points are the results of the numerics, and the solid line is the trace Widom to the GUE. So if now we plot the one for the boson, so if we want for the ASIP, we see that the asymptotic values are correctly captured. So they are similar. Seemingly there is a symmetry eta to minus eta, but the distribution is broader. Okay? How can we understand this? Huh? What is the relationship? Well, the relationship is our beloved way of looking at the dynamics of particles, that is to go from particle to interfaces. Okay? Or sometimes you do from interfaces to particle, I will maybe tell you. So this means that if we have a certain configuration of particle like this, we associate we in a sense introduce a certain height of an interface in the dual lattice, such that the variation of the height of the interface across two lattices is related to the number of particles. In practice, if I have this configuration, you see that going from here to here, there are three bosons, so you go down by 1/2 minus 3. Here, from here, there is 1, you go down of 1/2. From here to here, there is nothing, you go up. So you can construct a relationship between a configuration of particles and an interface. So now I simply reproduce this configuration here. When a particle jumps, essentially, what happens if the particle jumps here, this point actually goes up, because this is the number of the descent is reduced here, and this increased here. So it is essentially as you would have deposited a particle exactly where the jump occurred, okay? So note that the observable we are interested in, that is the number of transported particles, is just the height of the 0 plus 1/2 site of this interface, this equivalent interface. And with that, for example, I can show you the dynamics of the ASIP. Here I have prepared the bosons in such a way that there is one boson is followed by a hole, then there is another boson, then a hole, then another boson, then a hole. So it means that the starting interface will be up and down, up and down, up and down, up and down, with wigglings 1/2, so a flat interface. So if we run the dynamics, this dynamics, in terms of the dynamics of the interface, is what you see there, okay? Now, I told you there is a movie, we watched this till the end. No, okay, you understood the Now, okay, so let's take again the step initial condition. Let me show you what happens for the fermions. So this is our, in terms of particle, this is in terms of surface. So this is the corner erosion of a surface, okay? About erosion we will discuss in a second. So, and then it goes on, I mean, you see the interface departs from this slope corresponds to the longest, to the one this far apart. So for the bosons, instead, as I showed you, I mean, now in the case of a step, you see that the behavior of the interface is this, which looks markedly different in principle, no? Because, you know, you see that, you know, they seemingly don't share much, okay? But actually, this is not the case. How many minutes do I have? I think, okay, let me do brief quantum intermezzo. So I showed you that classical particle system we map into a classical interface. Sometimes you do the opposite. The classical interface can be mapped and studied. I mean, Herbert is a master of that in terms of the dynamics of particles, okay? So, but you can do it also at the quantum level. For example, what we have done in the past, we have studied the quantumism model in 2 dimensions. So there is an area of, you prepare it in the eigenstate of, prepare the state in the eigenstate of the operator sigma z, for example, such a way that here is up and here is down, so that you create a quantum interface in 1D. What we have done, we have exploited this mapping in the opposite way to study the dynamics of the quantum interface of the quantum interface in 1 dimension of the 2-dimensional Ising model can be mapped into a problem of quantum fermions in, sorry, here is 1D, not 2D, quantum fermions in 1D, subject to an external potential. These fermions, they show localization, Stark localization, exactly the same phenomenon for which tilting the lattice potential doesn't lead to transport. And then I show you, for example, here is the result. So imagine this is the part of your interface with spin down. This is the part of your, sorry, the part of your Ising model you spin down. This is the part of the Ising model you spin up. And when you do the dynamics, it's like this. It goes back because the dynamics is conservative. While in the previous case, there was a continuous erosion. If you want, details can be found here. So let's go back now to the classical problem. So I promised that we were going to end up in the KPZ. How do we see the KPZ? Well, I mean, I remind you that we introduced the height of the fluctuation in this way, and this is the observer we are interested in. It means on the continuum that essentially up to a factor 1/2, 1 is the derivative, the density is the derivative of the height, and that the observable we are interested in is the height at the origin. So if we do so, we take the stochastic Burger equations and we do the mapping to the Kardar-Parisi-Zhang. So we end up with the celebrated Kardar-Parisi-Zhang equation, where C takes the value of minus gamma. What is lambda? Now lambda, so this equation, as you know, it has the symmetry lambda h into minus lambda minus h. So in principle, this explains why we see things in the bosonic version and that are related to a change of eta. Okay? But let's say if we compare this equation with the stochastic Burger equation, it means that the coefficient lambda is actually negative for fermions, and we call it erosion. And we know that this is the Tracy-Widom to the Gaussian unitary ensemble. And if we have the bosons, instead the coupling is plus 2 gamma. So it has the opposite sign. So for the bosons, we expect growth. And therefore, we expect, again, the GUE. Because, I mean, this equation does not distinguish in practice eta to minus eta because it's a symmetry. When you do the numerics, actually, the result is different. So you have the GUE for Gaussian unitary ensemble for the fermions. What fits best the bosons is actually the GOE, so the Tracy-Widom distribution to the Gaussian orthogonal ensemble. So the question is, how comes? So this is a bit strange, no? Because the equation is the same, the equation has a symmetry. About erosion and growth, maybe we can discuss. So then we thought, well, what about the initial condition? Let's see what happens with the other initial condition. So if we take again the fermions and we do the ASEP, and you start with a flat initial condition, which means you put one fermion, one hole, one fermion, one hole, or one fermion, two hole, one fermion, two holes, I mean, is equivalent. There is the result that, I mean, and then the dynamics look like this. You start with this interface, and then it will evolve. The result is that it has to be Gaussian orthogonal ensemble for a flat, okay? If we start with a stationary distribution, that is, you occupy the sites with the equilibrium probability distribution corresponding to the stationary state of the process, you know that there is this back range, or come si pronuncia, or whatever you should say, distribution. And indeed, the numerics and the analytical are perfectly fine. What about now our boson case, the ASIP? So we start with a flat distribution. This is the evolution that you observe. And indeed, you end up with the GOE with the reverse sign of eta, which is fine. So now if we take the stationary distribution, remember it's more rough because there are these multiple occupied sites, you find indeed the back range with the flipped value. Okay? So what is this, the summary? So when we look at the fermions and ASEP, for the step, we find the Gaussian unitary ensemble. For the flat, the Gaussian orthogonal ensemble. For the stationary, the back range. Fine. This is well established, mathematician, Herbert, and all the company. If we do it for bosons, with a step, we got GOE again, and then back range. And then, okay, so these two are perfectly fine because one is, you get one from the other by simply flipping the sign of eta, which is fine, perfectly fine. But here, not. And then you say, how comes? But then our saviors came. Who is this guy here? Because, you know, there is this conjecture. Was, I mean, the fact, I mean, what they observe in this paper, Herbert and Prehofer, that when they study the pool and nuclear growth, which belongs to the KPZ universality class, so if the interface is curved, you get GUE. If the interface is flat, you get GOE. If it's stationary, you get BR, okay? And this matches with the first line, but seemingly doesn't match with the second line, okay? Now, just to show you, given that Katsuo is still here, you didn't show your experiment, I show you. So what this Prehofer and Spohn conjecture of any use? Yes, it is of any use. You go in his lab, and he was doing, I don't even attempt to explain what you did, but essentially was observing the growth of in a liquid crystal starting from a defect. So if the growth occurs circularly, or if the growth occurs in as a flat surface, what I discovered, if they study the height, there is a ballistic increase, and then the fluctuation to the ballistic increase turns out to be when the interface is flat of GOE nature, experimental data, or if the initial surface is roundish of GUE nature. Okay, so this is well-established experimentally. You know what? I'm almost finished my talk, but I've almost finished. So I've been faster than expected. But now, I mean, now if you look back, the only thing we could conclude is, oh God, we are a bit stupid. Why? Because, I mean, the result of Herbert is valid. I mean, it's a conjecture, but, you know, Herbert is always right. So, but if we look, remember the observable we are interested in is the height of the interface at the jump, no? The guys who have been transported. And indeed, you see that for the fermions, when you look at the height, this is locally curved. No? Because there is the natural curve. This curvature goes on forever in a scaling form. So locally here, the interface is always bent. But if you look at the case of ASIP, of our bosons, so you look here, so this is where we observe. You see that the place where we are looking for the observable we are interested in, that is the number of transported fermions, after a while ends up in a place where the interface is completely flat. And this is the reason why, even if we have an initial step, because of the shock wave which goes ahead, you observe the same distribution that you would observe in the ASEP when the interface is flat, okay? So this helped us in reconciling the two, okay? So I'm concluding. Incredible. I think it's the first talk that I finish ahead in my life, okay? My conclusion is that I showed you that when you have incoherent transport, and this was a big issue for my colleagues that will acknowledge at the end, they wanted to study this quantum system and they wanted to investigate it. So what I showed you is that this quantum model, then practically you can reduce it to a system of fermions that evolve like the ASEP, and about ASEP we know everything. Or in case of bosons, you end up with the so-called ASIP. But the ASIP and the ASEP, after all, up to minus changes in signs, so we have these two models. But if now we think of this model as a system of interfaces, what we have discovered that the fermions correspond to erosion. So to the Cardar-Parisi-Zhang equation with a negative sign of decoupling. The bosons, they correspond to the same KPZ with a positive sign, but anyhow, both of them, they are encompassed and represented by the KPZ universality class. So after 4 days of intense work, I think we should be relieved that universality saves us. And we are back in our comfort zone in which everything works. Although, I mean, as I said at the very beginning, when you look at the plot of the evolution, the dynamics of these two systems, they look completely different in a superficial way. And I mean, these things we published here this year. So I would like to thank then, okay, now I'll show you. This is the view from my office, just to tell you. So if you want to visit, you know where to find me. Here is downtown Trieste. And I have to thank, first of all, Yuri Minoguchi, who has been the driving force of the whole collaboration. He put me in contact with the other guys who are condensed matter physicists and quantum opticians around the world. And this guy, the guy who provided also the movies, so we have to be thankful to him for the movies. And then Julian Huber, this is the team in Austria. And this is the Peter Rabel and Louis Garber, this is the team in Munich. Herbert, probably you recognize the church here. And then I would like to thank you for your attention.
It's time for a lot of questions.
Okay, so thank you very much. Is there any initial condition that leads to GUE in this boson?
I was waiting this question. Yes. No, I mean, more than thinking about the initial condition, there is a simple trick. We didn't write it in the paper, unfortunately, but you know, it's rather simple, actually. Embarrassing simple. I show you here. If instead of counting the number of particles which crosses here, I go in the co-moving frame of the shock wave, I'm back to the KPZ. It's true that indeed we would like to find, we have been thinking if there is an initial condition that can sustain it seems not. But a simple trick to get GUE is simply not to consider the guys who have been to the left, but the guys who have been in front of the shock wave. Yes.
Well, what if,
KPZ is king and queen of everything here.
what if you start from a curved initial condition instead of wedge?
This we haven't done. So but the problem is that with these bosons, they are not really well behaving. You know? If you start with something like this, they try to, it moves and they accumulate, but we didn't do in detail. No, it's certainly interesting to try to see if without moving, without going in a co-moving frame, you can recover it. Yes.
Thank you.
Sorry, I'm not sure you should, but if you, can you compute something like analogous to height-height correlation or two-point correlation?
It's KPZ. I mean, we didn't do anything because after we realized that the fluctuating hydrodynamics is essentially KPZ.
So it's throughout KPZ.
What was giving a bit headache was this issue of plus or minus, no? Because, but you know, it's asymmetry, so it has to be asymmetry. So, and actually, the only thing, if you want that the fermions, they have one sign, the bosons have the opposite. That's why I mean, properly, I mean, this I have to ask the blessing of Herbert. We called it, I mean, this was what I kept. I mean, for our mnemonic help, we call them one erosion and the other growth. In the sense that, I mean, erosion, when you have a negative coupling of the KPZ, it means that when you deposit particles, actually what you are doing, you are consuming your interface. You have acid particle or hail, you know, when the hail. While growth, because when lambda is positive, indeed when you derive the KPZ equation, you always say lambda f, no? But lambda is positive, could be negative. It's more like the snow, no? Which is simply deposit. So this was the only thing to be realized. Then for the rest, unless, you know, maybe if you go to higher order correction, I have no idea. I mean, at this level, for this observable, these two models, though they look superficially quite different, they are all KPZ, one with positive and the other with negative sign.
So also one thing is you didn't have any Hamiltonian, right?
No.
So if you add
work in progress. This is work in progress.
But if you have
you can try to add coherence, but it's not. No, so if you want to re-add some quantum coherence,
then will it survive the KPZ or?
Given the time recorded, I'm not going to say anything.
Okay, thanks.
Hi. So in the noise term, I mean, in principle, it should contain also the, I mean,
the density.
Density.
It is not particularly relevant in practice. I mean, you can put it, but you see that nothing changes significantly. Because anyhow, you have always an average density, especially that is, we checked, doesn't change anything.
Okay.
In your table for the bosons, I mean, you had one column where you put bike vanes, and I mean, could you repeat what the explanation is for the bike vanes?
Ah, no, sorry. See, I'm half. No, I mean, here the explanation is simply that we know that this is true for fermions. I mean, it has been proved. For bosons, it's just, there is nothing spectacular. From the numerics, we find the Baker rates with the reverse sign, because these two models, they are simply related to a reversal.
Conditions come from, I mean, it should be stationary initial conditions for bike.
But we are taking the corresponding stationary. Yeah? So for the bosons, we take the corresponding stationary of the bosons. And for the fermions, we take the stationary of the fermion. This is fundamental, because otherwise it's not, no? No, I mean, this is a strong conjecture. I mean, this is, so in a sense, this is also a result, if you want. But you have to take the corresponding one. If you take it, you get exactly the minus theta of the other, because Cardar-Parisi-Zhang with plus is equal to minus the minus. Yes.
Yeah,
Yes.
thank you for the talk. This is a bit related to Mana's question, but do you think it could be realized in the lab? I mean, experimentally, these things?
This one?
Yeah.
The colleagues, they promised yes, of course.
They will do, or because sometimes they promise.
No,
but
they
eventually don't
always
do.
promise like this. I mean, I don't push them, you know, they promise like this. No, but I mean, the Hamiltonian, as I showed you, really, I mean, it's in the paper that I mentioned at the very beginning. It's a result. You sit down, you calculate, and you see that indeed you have if you have the coherence, the Hamiltonian part can be completely forgot, and problem becomes classical. So now, if you re-add coherence, who knows?
So do you think you can do it in higher D?
I can tell you about the quantum problem,
Yeah.
because this we have been trying to extend the case in the quantum problem, but you know, the problem is that you can. I mean, so the mapping from an interface to a particle, to a system particle, you can still do it. And in the quantum case, we have done it. The problem is that you end up with a two-dimensional quantum system which has kinetic constraints. Something that, I mean, you can do numerically, so there is no beauty. Now you ask the question. So because in the quantum case, but also the classical case, when you study these, the ASEP and the corner erosion of the ASEP, you discover that there is a relationship between the configuration of your system and the Young diagrams. Okay? And this was this very famous result of Okunkov, that if you take the Young diagrams with, now I don't remember the name of the distribution, with Plancherel distribution, you get a limit curve. Fundamental result, but why? Because if you undo the result, at the end you discover that the corresponding is essentially a system of free fermions. So you can get the fantastic mathematical result because behind essentially there is a system of free fermions that in 1D you can solve. In the other case, instead you get a 2D fermion, a system of 2D fermions, hardcore bosons, by the way, which is not, they are no longer the same. System of hardcore bosons, plus you have kinetical constraints. Indeed, so far we have done numerics. So,
in 2D, actually, I mean, Bloch, I mean, had these experiments.
yeah. No, I mean, yeah, I mean, for example, the case that I didn't tell about, I told you the quantum interfaces, there have been the group who did it. But then they were, I know they are recording, I'll tell you during dinner.
Okay, maybe I'll ask the last question. So, like, if this is on a ring, for the ASIP, I mean, at high density, is there some transition? Like, because it looks like at the same site you get some kind of a condensate. So
in the ASIP, yes.
Yeah, and ASIP, is there a transition?
I mean, I think most likely this ASIP is doing, I mean, what Satya studied N years ago and many others. There should be in the stationary state a condensation, but in our case we were interested in the transient.
Okay.
No, it's very likely that there is a condensation, no? Because you see it, there is one guy. How it occurs dynamic, I don't know. I don't remember where it was studied at the time. Was it studied? The dynamic formation of the condensate in, yeah, so. But, yeah. It also, in our case, there is the jump also, no? That
right, yeah.
creates and lose.
Okay. But at high densities, you might imagine it, because there's the transition rate increases, right?
Yeah. No, this we did, I mean, we were always, yes,
yeah.
Yes.
Right, yeah.
Hopping rate with 1 plus in I, whatever, I don't know if there will be condensate.
This has to be checked.
Okay, I think
Okay,
it was good to have time, and so thanks for a fantastic.
And I kept Satya awake. That was my